So the entropy is known as a measure of molecule randomness or disorder. The definition of entropy, typically we'll write delta S is going to equals to the Q over T, where the Q is defined as heat. The T is actually the temperature in Kelvin. For a system, every time when we write delta S, it means actually if you calculate entropy in the final state minus the entropy in the initial state. Assuming today I have a system, inside this system, I have a hot water. Let's say I have 100 degrees C water. And then I put these things in a surrounding where the surrounding is 0 degrees C cold water. So I'm going to put my system into my surroundings so that I can actually have my universe. Okay, so one is actually hot, 100 degrees C hot water into a 0 degrees C cold water. When I do these things, when I dump my hot water into my cold water, there'll be going to be some heat change. The heat is going to transfer from your hot water and goes into your cold water. So assuming that heat transfer is Q, then I want to calculate the delta S system. So I want to calculate the change of entropy of my system. We say the entropy was defined as Q over T, right? So since right now your system is actually giving out the entropy to your surrounding, right? Because the heat need to go from the hot to the cold. So heat is actually transferred from your system to your surrounding. Therefore, when we actually write out these things, we can write out our delta S system is negative Q over T, right? And the Q, we put an absolute value of it, so it's actually positive for the Q. So this is actually going to be your delta S system. So the T is not a random T, right? It's actually the original temperature. It's T1, okay? In this case, actually, 100 degrees C is 373 K, right? So that's actually my delta S system. Okay, is negative Q, okay, over 337. And then the delta S of your surrounding, okay, is going to equals to, since there's actually a Q that goes into the surrounding, okay, therefore the delta S surrounding on the top is also your Q, okay, but it's positive, right? And then you want to divide by the temperature of your surrounding, which is T2. 0 degrees C, therefore, is 273. Okay, so that's actually your delta S surrounding. From here, you can calculate your delta S universe, which is actually the sum of the two, right? Which is negative Q over 373 plus Q over 273. So right now, I have a question for you. Your delta S universe, is it positive, negative, or zero? Positive. Right, because Q is the same, right? And then you have the smaller denominator, therefore this term is bigger than that term, right? So you know your delta S universe has to be positive. So remember we said in the very beginning, if your delta S universe is positive, this process will happen spontaneously. Right? Makes sense, right? But it's even simpler than you thought, right? Because you know when you mix a hot water with a cold water, you know the heat transfer will happen spontaneously, right? The final temperature should fall in between these two extremes, right? That's what we learn. Okay, even if you don't know any of the thermodynamics, okay, you can already say these things out. What thermodynamics do is actually they convert those concepts, okay, into equations, and then you can use these equations to predict a more complicated case. If you can calculate your delta S universe based on the sign of your delta S universe, you can know whether this thing is going to happen spontaneous or not. Put these things into a more numerical form. So we're going to calculate a few things here. So this is also some questions you're going to see a lot in your homework. Calculate the delta S naught of the system. So every time when you see this little things on the top right corner. What it means, actually, the reaction is actually done in the standard condition. Every time when you heard this word standard condition, that means it's done in 25 degrees C, 1 atm pressure, and the concentration of all species is going to equal to 1 m. If you want to calculate the delta S naught of the system, so delta S naught of the system, the things you need to do is actually very simple. Just like you calculate your entropy, it will be the sum of the S naught of your product. Okay, of course, you need to actually multiply the coefficient of your product minus the sum of the entropy of your reactant multiply the coefficient of your reactant. We know what you really need to do is actually you want to find out the entropy of your H2O, multiply the coefficient, which is 2, minus the entropy of your reactant, in this case is H2, multiply its coefficient 2 plus 1 times the entropy of your O2. This is actually distant, that is actually latent. So this will be 2 times 189 minus 2 times 131 plus 1 times 205. Then you can get a number of 378 minus 262, 205. So this actually equals to negative 89 joules per mole. Okay, so let's say delta S naught of your system. So calculation-wise, it's actually very straightforward, very simple. Then I want to ask you one question. What is the delta S naught of H2O might becoming H2 and 1/2 of your O2? How do we calculate this? It's the same, right? So you just use your S naught of your H2 plus 1/2 the S naught of your O2 minus your S naught of your H2O. Okay, the same calculations, but easier way is actually, you can see the things I do here is actually I flip the reactions, right? And I divide by half. Therefore, you know the delta S naught of this one was simply equals to negative delta S naught of your original, then divided by 2. So there will be negative 89 divided by 2. That's going to give you a value of 44.5. So you should see the things, the entropy terms is an extensive property. If you change the coefficients, the delta S of that reaction will change accordingly. But in general, this is actually equations you can always use to calculate the entropy of a system. We want to actually connect the free energy delta G to your delta S universe. So in the very beginning, we say delta S systems plus your delta S surroundings. They give you the delta S of universe. That's actually the definition we got in the very beginning. Let's look at this specific reaction, okay? So H2O in the liquid form that goes into the vapor form. But we actually can describe these things using this very general definition we got. If this is going to happen, one thing we can know for sure is that your delta S surrounding must do something. If you want to actually make your water going from the liquid form to the gas form, what's going to happen is actually your surrounding will actually provide heat. Okay, you heat your water, therefore it can evaporize. So for water to evaporize, okay, we know you need to actually provide that much heat, right? So from the measurement, you know how much heat you need to actually provide to your system so that the water in your system feel the heat, have the energy, therefore it evaporizes. So you know that's how much heat you are going to dumping into your system. And because it is dumping into your system, to the surrounding, that means actually it's going to consume very much heat so that the heat can go to the system. And then eventually you need to divide it by your temperature so that it becomes the entropy, right? So this term can be rewritten as this. And then this actually, we just write the things again. Okay, delta S universe What we do next is actually we multiply this on both sides. And then what we're going to have is actually negative T delta S system plus delta H evaporations is going to equals to negative T times delta S universe. This turns, okay, negative T times your delta S universe was then be defined as your delta G of your system. And then left-hand side is going to become delta H evaporations, okay, minus T times your delta S of your system. These equations I just circled, okay, represents the delta G equations for the evaporation process. Later on, people actually generalize these equations, not just for the evaporations. For any chemical reactions, you can write the delta G in a very similar form. So that you got this delta G equals delta H minus T delta S term. So this is the most important equations of this chapter. Delta G equals to delta H minus T delta S. This is the equation you really need to actually memorize it. The important thing is actually that previous we say if your delta S universe is positive, then you have spontaneous reaction. Since your delta G is negative T times your delta S universe, temperature is always positive. Therefore, your delta G for a spontaneous reaction will always be negative. So if today, for a chemical reaction, if you tell you the G naught of your reactants and product, then you can calculate your delta G naught, which is actually your G naught product minus your G naught reactant. Then this thing is going to become negative, right? So here, the condition one we have is actually your G naught product is smaller than your G naught reactant. Delta G naught means free energy differences from your product and reactant, right? It's actually G naught product minus your G naught reactant. If in this case we know that delta G naught is going to become negative, okay, and this is actually the time you are going to have spontaneous reaction. Okay, you expect that to happen. That means actually you are going to have more product to form. On the other hand, if your delta G naught product is larger than the delta G naught of your reactant, your delta G naught again is your G naught of product minus your G naught of your reactant. It will be positive. Then it is a non-spontaneous reaction toward the product side. But what it means is actually the reverse reaction will be spontaneous. Okay, in other words, you are going to have more reactants. Previously, we always tell you, okay, delta S universe, if it is positive, then you have spontaneous reaction. Right now, you also need to remember, if your delta G or delta G naught is negative, then you have spontaneous reaction. Okay, so these are the two key things that you need to actually memorize for this chapter. One thing you're going to see a lot in your homework is that it asks you when the spontaneity of the reaction is going to change. What it really means is actually they want you to know if your delta G naught is equal to 0, okay, that's the point where your spontaneity is going to change, right? Because if it's larger than 0, it's non-spontaneous for your delta G naught, right? But if it's actually less than 0, then it's spontaneous. Then the delta G naught, if it equals 0, is actually a transition point. Okay? Now the question is actually, what is that point? What is delta G naught equals to 0? It's neither spontaneous nor non-spontaneous, right? So a very important concept that you need to know when you see this delta G equals to 0, it actually tells you that your system is at equilibrium. Okay, so it can go both ways. Let's refresh our memory again. For a spontaneous process, Your delta S universe need to be larger than 0. Your delta G need to be negative. Your system will be actually at equilibrium if your delta G equals to 0. Okay, so those are the 3 very important physical concepts that you need to have for this chapter.